It's my great honor to introduce our today's speaker, Professor Carlos Kenig from University of Chicago. Uh, Indeed, is uh, a world-renowned authority in harmonic analysis and PDs, and he's going to talk on solitons and channels of energy for nonlinear waves. Uh, Please join me in welcoming Professor Carlos Kenig.
Thank you. Thank you very much for the introduction and the kind invitation. It's always a pleasure for me to visit China. I first came to China in 1984, so it's a very long time ago. Beijing was a very different kind of town in those days. Anyway, I've always enjoyed being here. So the talk today is kind of an allegory for my scientific trajectory. So let me explain what I mean for this. I started out studying harmonic analysis and Fourier analysis. And then I started from there getting interested in linear partial differential equations using Fourier analytic methods. And eventually I became interested in nonlinear partial differential equations using techniques from everywhere. And so this talk kind of is meant to show that progression in some sense. Okay? Let me see. Do I have to be here to move or can I move around? Well, let's see if it works. Okay, so I start with the slide. Fourier analysis and partial differential equations have been intertwined since their very beginnings in the work of Joseph Fourier, 1768 to 1830. So Fourier was an amazing mathematician. He was also a politician. He was a viceroy of Napoleon in Egypt. So he governed Egypt for a long period of time. But he also studied the mathematical theory of heat conduction. And his study in 1807 led him to derive an equation, which we now call the heat equation, to describe the heat flow in a one-dimensional bar. His starting point for this was Newton's cooling law, which says that the temperature flux through a point is proportional to the temperature gradient at that point. So the heat equation is the partial differential equation, time derivative of u minus second spatial derivative of u equal to 0. Okay, very well-known heat equation. And given the initial temperature of an, let's say, infinite bar, and let's assume that the temperature is 0 near spatial infinity, what Fourier was able to do is calculate the temperature u at any point in the bar for any future time. Okay, so they give you the initial temperature, and then you know the temperature in the future. Okay, and to do that, you have to solve this heat equation. So Fourier invented Fourier analysis to solve this problem. Okay. So in the course of this calculation for the temperature, Fourier made a very bold claim, and this motivated a lot of the study of Fourier analysis in the centuries after that. And Fourier's claim was the following. Suppose you have a function u0 on the line, and let's assume that the function is 0 near infinity to simplify matters. Then you can represent it as an integral of trigonometric functions. That is to say, the function u of x is the integral between minus infinity and plus infinity of a function c of xi times this trigonometric function cosine 2 pi I x times xi plus I sine of 2 pi x times xi, and you integrate dxi. And he also gave a recipe to calculate this function c of xi in terms of u0. So it's 1 over 2 pi integral between minus infinity and plus infinity, u0 of x cosine 2 pi x xi minus I sine 2 pi x c dxi. Okay? So this was Fourier's claim that every function can be written this way. And now we denote this coefficient c of xi, u0 hat of xi, the Fourier transform of u0. Okay? Now, this claim of Fourier was extremely controversial. Why? Well, the functions cosine 2 pi x xi and sine of 2 pi x xi are very nice functions, right? They're infinitely differentiable, they're very smooth, very regular. So how can it be that any nasty function, let's say u0, can be written as an integral, which is a glorified sum of nice functions? This did not make sense to many people at the time. And it turns out that, in fact, it is not correct. It is not true that this happens for all functions. But for many functions, it does happen. And so Fourier wasn't stopped by this, and he moved on. And we're still trying to understand completely for which functions this can be done, especially in higher dimensional settings. So these are problems in Fourier analysis that still have to be resolved. Okay. So why did Fourier use this idea of decomposing your function as an integral of trigonometric functions? His basic idea is that there is a simplification in solving the heat equation. That you don't have to solve the heat equation for all data, but just for very special data. And then you can put it together by using this Fourier decomposition. So it's enough to solve it for these trigonometric functions, cosine 2 pi x c plus I sine 2 pi x c, represent plane waves. And then if you solve it for this one, you get the general solution by integration in the parameter xi against the function c of xi. So for the heat equation, for the above u0, we can calculate explicitly what the solution is. It's e to the minus t 4 pi squared xi squared cosine of 2 pi x xi plus I sine 2 pi x xi. So this gives you the general formula for the solution of the heat equation by using the Fourier representation of functions. Okay. So even though Fourier's claim has turned out to be false for all functions u sub 0 and all points x, Fourier's method worked. He wasn't stopped by this. The method works and very quickly yielded very important applications that empowered the great technological advances of the 19th century. Yes? Yes. So let me give you some of the examples that were achieved through Fourier's method. The first one is the calculation of the temperature of the Earth. So suppose you know the distribution of the temperature on the surface of the Earth. How do you find the temperature inside? The answer is you solve the heat equation. Okay? The second, and this was due to Kelvin, is the prediction of tides. So this was a very important advance in navigation and commerce in the 19th century. If you could tell when the tides would come, you could tell when you have to set sail or not. Okay? So this was a very important advance, practical advance. The next example that I'd like to mention is the construction of the transatlantic cable. So in the United Kingdom, there was an effort to try to join telegraphically the United Kingdom with North America, with the United States. And so there was a licitation, and some company won the licitation to construct this cable that would allow for this transatlantic communications. And so they had some scientists who worked for the company who designed what thickness the cable had to have. And they built a cable that crossed the Atlantic. And they put it down, and then they tried it, and of course nothing happened. No communication. So then they realized that somehow something had gone wrong, obviously, and so they needed somebody very good at science to design the cable. And they asked Lord Kelvin to do this. And Kelvin was a very smart person. He was one of the great scientists of all times. And he was able to figure out that what the problem was that the width of the cable had been wrong. And that he used Fourier analysis to calculate the actual width that was needed. And so they built the new cable, and they threw it down, and it worked. And that started the communication across continents. Okay? And this is, again, thanks to Fourier analysis. Okay. I must admit that I'm partial to Fourier analysis. Okay? So another interesting thing that happened around the same time was the calculation of the age of the Earth. So there's a way to use Fourier analysis to determine how old was the Earth with a small error. So the Fourier representation of functions indeed holds for many functions. If you have sufficient smoothness on the function u0, you can certainly do it. And this, besides the great technological uses of this idea, theoretically, it was of fundamental importance in the study of linear partial differential equations in the 20th century. The 20th century saw a big revolution in the study of linear partial differential equations through the work of many people like Nirenberg, Hormander, Calderon, and many others made many important advances. But linearity is essential for this, and we all should know that the world is not linear. So now let's go to nonlinear partial differential equations. So the idea of Fourier was to find a simplification on how to solve linear PDEs. Now I'm going to talk about a different class of equations, which are nonlinear, and they're the dispersive equations. And for this class of nonlinear equations, there will also be, or hopefully also be, a simplification. So a way to find out how solutions behave for very large time. Okay? And so this is an asymptotic simplification. And these dispersive equations appear in nonlinear wave propagation. And I have spent the last 36 years studying these equations. Okay. And I hope for some more. I'll continue. Okay. So let me tell you a few things about nonlinear dispersive equations. So nonlinear dispersive equations are time reversible. So time can go both backwards and forwards, and like the heat equation, which goes only forward. Okay? So the linear cases of these dispersive equations can also be solved by Fourier's method. And in fact, Fourier's ideas are, and the representation are fundamental in the study of linear dispersive equations and also nonlinear dispersive equations. Typically, these dispersive equations have an energy that is conserved, so there's preservation of energy, but the energy could be both positive and negative. Okay, so this is kind of unintuitive, but there can be negative energy. These equations appear, for instance, in the study of shallow water waves, in channels, for example. Lasers, which I'm using right here in the pointer. Actually, I'm not using it, but in the pointers, lasers are used every day in many things. And they arose as a consequence of the study of the nonlinear Schrödinger equation, which is not something I'm going to discuss today. But other things in which they're used are nonlinear optics, nonlinear elasticity, particle physics, general relativity, and also in geometric contexts associated to this. Okay? So these equations are now being studied very extensively, but they were first introduced in the 19th century. So in my opinion, this is currently one of the most exciting areas in PDE. So I'll mention some examples. The generalized Corvec-de Vries equations. So this is a family of equations which can be used to study water waves in shallow channels. Okay, and those are studied experimentally and theoretically using these Corvec-de Vries equations. I'll say more about this in a few minutes. There's the nonlinear wave equations, which arise in nonlinear elasticity, in particle physics, in general relativity. And I will emphasize later on something called the energy critical case. And I'll explain what criticality means here. And the notion of criticality that I'm going to discuss has to do with scaling. Criticality with respect to scaling. There are other notions of criticality, but the ones that I'm using here is with respect to scaling. So why are these equations called dispersive? Okay, you know that mathematicians are very simple-minded when naming things. So these nonlinear equations are dispersive when the linear equations associated to them are dispersive. Okay, so when are linear dispersive equations dispersive? So heuristically, and you can tell if an equation is dispersive when the flow, as time goes out, you spread out the solution. So you make the support bigger and bigger. You push out. Now, because they have a conserved energy, so that means that some quadratic quantity is constant, but the function support is spread out, it means that it forces the function to be smaller and smaller with time. Okay, so that the constant remains constant. And so this is what people call the dispersive effect. In fact, it should be called the linear dispersive effect. The fact that as time goes by, the size of the solution becomes small. Okay? The nonlinear versions have solutions that may not be dispersive. So non-dispersive equations, non-dispersive solutions. For example, solutions that are static, constants, or traveling wave solutions. These are solutions which are always the same shape and travel and evolved by traveling in time. And the well-known solitons, right? Solutions of the form u of x comma t equal to u of x minus c times t. And some of the nonlinear equations have solutions of this form. Okay. Now, the existence of solitons has been a mystery since they were discovered in the 19th century. They were discovered in the 19th century by John Scott Russell, a Scottish engineer, who first saw such a traveling wave in a canal in Scotland and chased it on horseback for many, many miles and saw that it didn't change shape. It just evolved by translation. Now, Russell wasn't an ordinary engineer. He is not what we call an engineer nowadays. He was a member of the Royal Society, for example. So he was a well-accepted scientist. And he also was the engineer that designed the biggest steamboat from the early 19th century until the beginning of the 20th century. That was Russell's boat. So this guy was not a fool. He knew what he was doing. Now, Airy and Stokes, who were very prominent applied mathematicians in the United Kingdom, said that this solitons couldn't exist because they had theories of water waves that were linear, and they could not explain these solitons. But later on, Boussinesq in France and Rayleigh in the UK put forward nonlinear theories to explain Russell's observations. And finally, at the end of the 19th century, Korteweg and de Vries formulated the Korteweg-de Vries equation in 1985 that explained the existence of solitons. Okay. Okay, so let me go back to the general theory of dispersive equations. After early works in the late 70s and 80s, in the late 1980s and early 90s, with Ponce and Vega, we introduced the systematic use of the machinery of modern Fourier analysis to study the linear dispersive equations and to use those estimates that we obtained for the linear dispersive equations perturbatively to understand the associated nonlinear problems. And this really transformed the subject. And the resulting body of techniques with refinements and extensions by people like Bourgain, Tao, Tataru, and many others, gave far-reaching theories on the local in time existence of solutions to nonlinear dispersive equations and the global in time existence for small data. So in the perturbative regimes, you could pass from the estimates in the linear problems to the nonlinear regime. Okay? Okay, so far so good. But then the last 20 years have seen an emphasis on the study of the long time behavior of large solutions to the nonlinear problems. So we want to get away from the perturbative regime. Okay? And a special class of equations that we have been studying in the large are the so-called scaling critical cases. And I will explain more precisely what this means. And this study was transformed by work that I did with Frank Merrill in the period 2005 to 2009. And we developed a method which has now become the so-called standard approach to this kind of problems. So the ultimate goal of the Kenig-Merrill method was to attack the problem of asymptotic soliton resolution. So let me tell you about this. What is this asymptotic soliton resolution? Since the 1970s, there has been a widely held belief in the math physics community that coherent structures, things called coherent structures, and free radiation describe the long-time behavior of solutions to nonlinear dispersive equations. Okay? So this is not a conjecture, but a belief. Okay? And this belief came to be known as the soliton resolution conjecture. So this is not a conjecture in the precise mathematical sense, but it's more a belief. Okay? So what does this belief say? Roughly speaking, it says that asymptotically in time, if you follow the evolution of your dispersive, nonlinear dispersive equation, if you wait long enough, the evolution decouples as a sum of tuned traveling wave solutions, solitons, and a free radiation term, which is a dispersive term in the linear dispersive sense, something that will go to zero locally in space, solving an associated linear equation. So this is what the soliton resolution conjecture postulates. Okay. So this beautiful claim postulates an asymptotic simplification, because you start out with whatever initial data, and then you evolve in time. You wait long enough. First you enter in some kind of black box. You don't know what's going on inside. And then if you wait long enough, then you get a sum of solitons plus a linear term asymptotically. Okay? So it tells you that this very complicated long-time dynamics resolves into something which is relatively simple. So why did people make this conjecture? So this is a nice story. And it goes back to the end of World War II, to a puzzling numerical simulation by Fermi, Pastel, and Ulam at Los Alamos. So this was after they had created the atomic bomb, and they had a big computer, big for those days. I mean, today everything that they could do can be done with a laptop very easily. But anyway, so they called it the Maniac, was their big computer that did the calculations for the Manhattan Project. And Fermi decided that a great use for this machine was to use it for theoretical scientific purposes. So Fermi decided that he wanted to do a numerical experiment in this computer to analyze the solutions of a PDE. And this was the birth of scientific computation. So this was the first scientific computation ever created. And it was done by Fermi and his team. And so what did they find? Fermi wanted to do an experiment to verify the principle of thermalization. I will explain what that principle is. They considered a nonlinear vibrating string modeled by discretization in a lattice, I mean, one-dimensional, okay? And Fermi expected that even if the energy is initially concentrated in one mode, instantaneously it would be equidistributed on all modes. And that's what was called thermalization. And that's what Fermi expected. But the simulation showed, to Fermi's surprise, that this need not happen. It could be that the energy keeps being concentrated in one mode. Okay? And Fermi was surprised, and he called this a minor discovery. And this is it's very interesting to read about this in Ulam's autobiography. Okay. Of course, he did a minor discovery, in particular of scientific computation. But okay, so everything is in the perspective. In Fermi's perspective, this was minor. Okay. So Fermi, like everybody else on his team, died soon after. They all died from radiation-induced cancer. And this mystery remained for quite a while. In the mid-1960s, somebody else who was very smart, Martin Kruskal, made the observation that if you take the mesh that they used in the Fermi-Pasta-Ulam experiment and you let it go to zero, the Fermi-Pasta-Ulam model converges to the corrective Riesz equation. Okay, first observation. Okay, but the corrective Riesz equation has traveling wave solutions. That was what Russell discovered in his report. Okay, and if you think about it, if you have a traveling wave solution, thermalization cannot happen because it's of the form u of x minus ct. You take the Fourier transform of this, you're multiplying by something of absolute value 1, so the size or the modes remain the same. They remain constant in time. So thermalization cannot happen if you have a traveling wave solution. And that was the first explanation to the Fermi-Pasta-Ulam paradox. So that's why thermalization does not occur. Okay. So Kruskal and Zabusky in the mid-60s did their own numerical computation. They had better computers than the MANIAC by this time. And they discovered two very remarkable facts. The things that I put in quotation marks is because they're not mathematical facts, they're experimental facts. Okay? So the first fact is that if you start with data concentrated, let's say, in just one mode, the evolution for large time is a sum of solitons. So they computed the solution for large time, and they see that it's a sum of solitons. So this is what led to the soliton resolution conjecture. Okay. The second fact that they discovered with other data, so instead of taking data in one mode, they constructed data which is the sum of two solitons which travel at different speeds. Okay, two of them. So as they evolve, they're going to collide, right? This is what's going to happen. So eventually the solitons collide, but remarkably, after they collide, they reappear with the same shape. Maybe they got translated, but they have the same shape. And this is something that one would expect only about linear problems, but this is a nonlinear problem, so this was very surprising. And now this led to the theory of complete integrability. So integrable systems and so on. And this is an important concept in nonlinear science that emerged from this second experiment of Kruskal and Zabusky. Now, I'm not going to define integrable equations rigorously, but just to give you a feeling for it, these are equations which are nonlinear, but which can be reduced to a collection of linear problems. Not PDE problems, but a kind of a reconstruction of the spectrum problems. Okay. And integrability is a very non-generic phenomenon. If you have an integrable equation, you move it a little bit, it will no longer be integrable. Nevertheless, this kind of equations arise remarkably in many physical settings. Okay? But they're not generic. And so I say here, I used this. Okay, I used the laser. All right. So for the family of KdV equations, the first two are integrable and not the others. The nonlinear wave equation, the ones that I'm talking about, are not integrable. And so there are many more equations that are not integrable than the ones that are integrable. Okay. So soliton resolution has been improved in a few integrable cases. For instance, in KdV, in the second one in the KdV list, and in some others, nonlinear Schrödinger equations in one dimension with cubic nonlinearity, for example. But the quest for establishing soliton resolution for any non-integrable nonlinear dispersive equation has been a grand challenge in PDE for over 50 years. Okay? So the impasse was broken for the first time in a time reversible PDE in the work we did with Ducaire and Merrill in 2013 on the three-dimensional radial energy critical wave equation. Okay, so far I have avoided writing equations. I have to start writing some equations. Okay. One dimensional. Yeah. Yes. Of course. But here we have a little bit of a hybrid situation because we're talking about 3D, but radial. Okay? Okay. So let me explain what we did. But so I'm going to give some philosophical reasoning for this. So the mechanism for relaxation to a coherent structure. What is a coherent structure? A finite sum of solitons. Okay, that's what a coherent structure is in this context. And such a mechanism was observed numerically and experimentally, is the radiation of excess energy to spatial infinity. So as you evolve, you push away energy to spatial infinity. So for this to happen, you have to be working in an infinite rod or an infinite space-time, okay? And such a phenomenon appears in diverse settings experimentally, such as the dynamics of gas bubbles in a compressible fluid. This you can see in a lab. You can see the solitons. And in the formation of black holes in gravitational collapse. Now this has to be seen numerically, of course, because if we observe gravitational collapse in real life, we're no longer here. Okay. All right. And we were able in this work to quantify mathematically this phenomenon. Okay. I'll explain this in a minute. So now come the formulas, okay? So I'm going to consider the nonlinear wave equation. So this is the usual D'Alembertian equation, and this is the nonlinear part. When we're talking about R3, this energy critical nonlinearity is u to the 5. And if you are working in Rn, it gets more complicated. And you can see that when n equals 3, this is u to the 5th. Okay. When n equals 4 is u cubed. And then for higher, you get fractional powers. Okay. Now this is an equation that we call focusing, because the linear and the nonlinear terms have the same strength, but opposite signs. Minus the Laplacian is a positive operator, and u to the 5 has the plus sign there. So since they're equal, they fight each other. Okay? So the next thing I want to say about this equation is that it's energy critical. So that has to do with scaling. What does it mean? If you have a solution in the three-dimensional case and you perform this transformation where you scale space and time and you multiply by the right factor, then this is also a solution, even though the equation is nonlinear, okay? And it's energy critical because in the energy space, H1 cross L2, the size of the data is unchanged by this scaling. And that's why we call it energy critical. So by scaling, you cannot make the initial data small. Okay? This equation has a conserved energy. In the 3D case, it is this one. And in the general case, it's this. And now it turns out that this equation, which is a nonlinear dispersive equation, has solutions that do not disperse. Okay? So for example, solutions to this elliptic equation, Laplacian of q plus q to the 5 equal to 0, and in general these others, are static solutions to the nonlinear wave equation, so they cannot disperse because they don't move in time. Now this is a very interesting equation for geometers because it's the equation that governs the Yamabe problem in differential geometry. Okay? And this is the energy critical nonlinear wave equation. Now, among the solutions to this elliptic equation or to the nonlinear wave equation, there is one of least energy. In 3D, this is the formula, and in ND, there's an analogous formula. So it's a very simple formula for this object. And it's the one of least energy among the static solutions. And there's a gap. The next one has a jump in energy. Okay? And this one is called the ground state because it's the one of the least energy. Okay. So up to sign and scaling, they are the only ones of least energy. But there's also traveling wave solutions, solitons, for the nonlinear wave equation. And what they are is you perform a Lorentz transformation to a static solution. And then you get a traveling wave solution. Okay? So in R3, suppose that Q is a non-zero static solution. You do this kind of transformation, and you get, for all subluminal directions, you get a new traveling wave solution now, which moves in time. By here in this model, the speed of light is 1, and that's why this is subluminal. Okay? And with Ducaertz and Merle in 2014, we proved that these are all the traveling wave solutions for the nonlinear wave equation. Okay? So in the radial case, you cannot have a traveling wave solution because it destroys radiality once you do a Lorentz transformation. But you can have scalings and change of sign of the solution. And these are the only static solutions. Okay, these are known to be the only static solutions. So the theorem on soliton resolution was in 3D, and it says that there is a radial solution of the linear wave equation. That would be the radiation term. There are scaling factors that are well ordered, and the two less than or equal signs means that the ratio goes to 0 as time goes to infinity. Okay? And they're all much, much smaller than the speed of light, which is 1, and so they're much, much smaller than t, such that U is written as the sum of these rescaled static solutions with a plus or a minus, plus the linear term, the radiation term, plus an error that goes to 0 as time goes to infinity. And for the time derivative, you just get the derivative of the radiation term because these W's don't evolve in time. They're static solutions. So there's nothing there. So it tells you, it gives you the soliton resolution. The solitons are the rescaled W's, and all solutions eventually become a sum of rescaled W's plus small errors. Okay, so this is the soliton resolution conjecture. Okay, so I'm not going to give you the proof of this. That would be a killer. We'd be here until midnight. But let me just tell you one key fact in the proof. And this is what we call energy channels. Okay. So for radial solutions of the nonlinear wave equation, outside an enlarged light cone, there are two possibilities. Well, 0, that's not very interesting. You have plus or minus a rescaled static solution, or for all r bigger than 0, there is some energy outside of this fattened light cone. So that's why we see the excess energy in spatial infinity, because this thing is bounded below, either for positive time or for negative time. Pardon me? Gap in what sense?
I mean by fixing the gamma.
Who's gamma here? Eta? No, it's just there exists for each one of them an eta. Yeah. Okay. Because there are many radial solutions, so there's a continuum. So you can't have a fixed gap. Okay.
Yeah.
Okay. And but this quantifies the fact that at spatial infinity, there's always some energy. That's what this is saying, in one time direction. And this is the key ingredient for the proof. Okay. So we tried, so this was a three-dimensional thing, and we tried for a decade to extend this to higher dimensions. We thought it would be just a simple extension of this proof to higher dimensions, and we were completely wrong. And for example, in dimensions 5 and higher, this fact fails for some solutions, and they are in this fact is in some of the joint works with Charles Collot, Ducaerts, and Merrill from 2022. Okay, something like this cannot hold in the non-radial case. I mean, this is easy to see because of Lorentz transformations. But so we were stuck. So, when you're stuck, you have two choices. You just get stuck and you're stuck and you don't know what to do, or you try to do something maybe a little bit easier. So we tried that. We did something a little bit easier, and what we showed was that the analog of the theorem of this decomposition for n bigger than 3 did hold, but only for well-chosen sequences of time, for a well-chosen sequence of times. Not necessarily for all times, but for many sequences of times. And the first proof of such a result was by my then student Casey Rodriguez in 2014, who did it for odd dimensions. And then my postdoc Howard Gia and myself did this in 2015 for the even dimensions. And there's a substantial difference here between even and odd dimensions for wave equations because of the strong Huygens phenomenon and the finite speed of propagation. Okay. And then we were able to also prove a similar result in the non-radial case. Okay. And this was in joint work with Howard Gia, Ducaerts, and Merrill in 2017, where we showed that if U is a solution, non-radial, for dimensions between 3 and 5, then you can find the radiation term as solution of the linear wave equation, a well-chosen sequence of times, Tn, non-zero solution of the elliptic equation, Laplacian u plus, let's say, u to the 5 equal to 0, and vectors that give you the direction for the Lorentz transformation, scales, and positions. Okay, so all the parameters that need to be involved, such that a solution is written, again, as a sum of traveling waves plus a radiation term plus a small error. And now when you go to the time, since these solutions depend on time now, possibly depend on time, you have to account for that. And so it's the corresponding thing. And then all these parameters are well separated in scale or in space, so that they are all independent of each other, these solitons. Okay? Okay, so we were very happy with this result. But a method of proof, which in this case was monotonicity as the time average, cannot give more than a decomposition for all well-chosen sequence of times. And there's examples. For example, there's an example due to topping in a very related geometric case, the harmonic map heat flow, where when you can find smooth targets for which the decomposition holds for subsequence, but not for all sequences. Okay. So how do you move forward from this? Okay. using the decomposition for well-chosen sequence of times from the first for these theorems, now we want to follow what happens in between those successive times that we've found. And what we eventually realized is what we need to understand is collisions between traveling wave solutions. What happens when, because they go at different speeds, the traveling waves start to collide? What happens? And what we came up is that in non-integrable cases, in not rigid cases like the integrable cases, there's always going to be radiation produced. So there's always going to be energy produced by collision of the traveling waves. That's what we tried. That's what we realized is the key to proving the full soliton resolution, not for just sequences of time. And this is contrary to the Kruskal-Zabusky numerics in the integrable case, because in the integrable case, when they collided, they came out cleanly. And here we're saying that what should happen in non-integrable cases is that there should be energy produced. There should be radiation produced outside. Okay? So I will conclude with theorem 4, which is that the analog of theorem 1 does hold for radial solutions of the nonlinear wave equations for all dimensions and bigger than or equal to 3. The odd case in which the Huygens principle is strong, which is the more favorable situation. We proved this in a paper that appeared in 2019. It was just before the pandemic. Then in the first even dimensional case, in the paper with also with Ivan Martel in 2021, this was a pandemic paper. We were working through the pandemic. We were all home. We had nothing better to do. So we proved soliton resolution. So the even dimensional cases turned out to be harder than the odd dimensional cases because of the difference between the strong Huygens principle and the Huygens principle. Okay. The n equals 6 case was done in early 2022, and then our former postdoc and student of the Karen Merrill and my student with Schlag in late 2022, they did all dimensions bigger than or equal to 4. So all even dimensions. Okay, so I have a few more slides. Thank you.
Thank you so much. Any question?
I have a question. This mentioned gravitational collapse. Can you repeat how it is relevant to gravitational collapse?
Could you say that?
You mentioned gravitational collapse.
Yes.
So how it is relevant? Can you repeat again?
Yeah, so what I said is that in cases of gravitational collapse, you can see numerically the decomposition.
We have binary black hole data.
Yeah. Yes. Yes, and but besides that, you can have more than one. right? You can have several black holes, and that would be the solitons.
Okay. More questions? Oh,
Yeah.
Very your first and second action, the first part is really on linear equation and the method and further analysis.
Yeah.
Very suitable for linear 2D, and the second one is on harmonic equation. So how is connected is really on the next.
Yeah. Well, a starting point that you need to be able to do the estimates in this is the estimates that happen in the linear dispersive equations. And so that's the connection.
So for nonlinear program, what kind of modification?
Well, you have to change completely, but the tools that you use in those changes are no. We use both physical and Fourier space. Okay. You need both. Yeah. Yes.
Can I try? Correct me if I'm wrong. So, do I understand you correctly that you say that in the not some non-integral cases, solution of the system is sum of traveling waves at usual solitons that has kind of elastic collisions or not?
Inelastic.
Inelastic. But still, after collisions, you have again tidal wave-like solutions.
Right, but what changes is the radiation. There's a radiation term always, not just pure solitons.
Yeah, you need some corrections.
Yeah.
So it's kind of background.
Right.
Yes.
Right.
And you say that it happens for this class of general 2DV, and you expect that it's a general phenomenon for all non-linear equations?
For all dispersive equations, which are not integrable.
So you focus on these solutions. It looks like sum of traveling wave solutions. It's not kind of description of whole space of solutions.
No, it's supposed to be all space of solutions for large enough time. Not, we don't choose particular solutions.
So you say that general solution of this equation is some traveling wave, some background, and then this traveling waves interact in elastic wave.
Yes.
Thank you.
More questions? Regarding the general case of hidden dimensions, do your student follow the method you gave for n equals 6?
Okay, so there are two different answers to this. First, the work of Gendridge and Laurie uses the fact that there should be dispersion, that there should be something outside energy. Okay, so that the collisions create outside energy. But they don't use, that's the starting point, which is our starting point. But they use a different method called, let's see, what's the right word for the method? They use a more dynamical systems approach. Okay. But then one of my current students is doing it by our method. Pardon me?
I'm not quite knowledgeable in PD, so I'm always thinking about harmonic analysis.
Yes.
I know. And my question is that you started with the Fourier analysis in one,
Yeah.
and then, of course, what you mean by Fourier analysis? You mean what? You mean what colors are going to
Yeah.
need, and you know what they need.
Yes.
But our knowledge about higher dimensions
in Fourier analysis, it's very limited.
Of course.
Yeah. And then how these limitations affect to your works in the theory of
Yeah, so that's a fair question. We really don't know the answer to that, but my hunch is that they don't affect it at all.
Really?
Yeah.
That's the good news because we do not know.
No, because it's, you know, we talk, let's say, for instance, about the restriction theorem for the Fourier transform and related topics. And what seems to me is going to happen is that we will only need the L2 restriction theorem and this idea. But of course, I can be proven wrong. Has happened before. So.
Question? Yeah.
Do I understand correctly that you work always on the infinity boundaries? You never care about boundary conditions?
No, well, it's not that we don't care. But in periodic situation, you don't have dispersion in the same sense. And so it's a different story.
Semi-infinite boundary condition.
Uh,
I inspire from integrable cases, so I try to understand what you can take from there.
Yeah, I don't know the answer to that one. But in general, the periodic case doesn't produce this Soliton resolution because there's not enough dispersion.
Questions? Sure.
Very exact description of the solution equation with any complex
Well, I can tell you one thing first that we generally know, that if you look at solutions in the supercritical regime, where you assume that in the appropriate space they remain bounded for all time, then they'll behave linearly at infinity. There won't be any Soliton resolution. Okay? That is a general situation that we understand. Now, if you don't have boundedness of the norms, your guess is as good as anybody's. I don't know, but yeah. I still want to first understand the energy critical case fully. Now, what is another very interesting topic is to try to do a similar thing for the nonlinear Schrödinger equation. That is a very interesting topic. And there, since you don't have the finite speed of propagation, we really don't understand what to do.
Okay. So, no question. So let's thank Professor Kenig for his fantastic